I'm not sure why this presentation is in this session, but I think the plastic zone is important for every problems about fracture, especially if you have metallic materials, and therefore maybe if you have a closer look on the plastic zone, it will also help to minimize the risk and to maximize the safety. So we are looking on the plastic zone, and we have seen this model of the plastic zone several times during the conference so far, and I'm sure we will see it sometimes more here on this conference. And you know, in the middle of the plastic zone we have our plane strain condition. At the surface of our specimen we have our plane stress condition, and the plastic zone is smaller in the middle and it's larger at the surfaces, and this is very important if you determine the fracture toughness Kc for different thick specimen, because if you have a thin specimen then the fracture toughness is higher than for the thick specimen, and only for thick specimen you have a constant K1C value, and this is related to this plastic zone. So how does this plastic zone look like? Actually, we were not interested at the beginning in this three-dimensional shape of the plastic zone, because when my PhD students, I should mention Matthias Thielen and Florian Schäfer, who did these measurements at the synchrotron, we were interested in the effect of an overload during the fatigue, and by this we measured the stress in front of our crack tip. And from the synchrotron data then we got the idea that we have the information about the stresses in depth resolution also, not only in the surface but also in the depth. And this is what we found before the overload. It was in this case here you see the stress distribution at the surface, and if you go to deeper position then the plastic zone is increased, and according to the model it should be reduced if you're going deep inside, and this was then the last position measured at the beginning. And so we think this is not what we would have expected, and this was also found after the overload. Then the plastic zone is reduced due to the residual stresses after the overload. But we will focus here on this. And what we also did was digital image correlation, which is again on the surface where we expect to have the plane stress state, and if we compare the shape of the plastic zone with the shape we expect from calculations from literature for plane stress and for plane strain, it doesn't look like plane stress, a little bit more like plane strain. So it's not what we expected. And if you have a look also in literature, you will find for 2D here you have plane stress, and for 2D simulation for plane strain, then the plastic zone and the stress distribution is increased at the surface and it's smaller in the middle of your specimen as you expect from the model. But if you make the same for 3D calculations for different thick specimens, then you see this is at the surface and this is below the surface, and the plastic zone, the stress distribution increases, and this you find for different thick specimens. So we think then having a closer look on our data from the synchrotron will help us to get an idea of the 3D shape of the plastic zone, and this is what we have done with our experiments. So this may be the plastic zone. If you take it from these simulations, you will find something like a hump here in your stress distribution and the plastic zone below the surface, and the question is, can we find this also in our synchrotron experiments? If you want to measure the plastic zone, the stress distribution, you have different options. You can measure it by digital image correlation, then you get only the information from the surface. Or you can measure it by XRD in transmission, then you get the information through the whole specimen, but you can only do this for very thin specimen. Or what we have also done, we measured the stresses in front of the crack tip by Barkhausen noise, but this is not so easy. You have also some information of the depth, not only surface information, but this is quite complex to be calibrated, so it's not so easy to get the information here from this. Therefore, now we have our synchrotron data, and what can we do by this? First, we have special resolution of 100 microns. So we measure step by step, and 3D, or at the beginning, the 2D shape of the plastic zone, or the 2D shape of the stress distribution in front of the crack tip by a stress mapping. We can do this by in situ testing. So we have a pre-fatigued specimen, and then we load it in the synchrotron, and then we can measure the stress distribution in front of this crack. And now what's about the information depth? Well, the XRD, here you have the peaks for the different planes in your crystal, and these peaks you get at different energies. And different energy, higher energy, means you have a higher information depth because of the absorption of the X-rays in your specimen. And if you do this, then you get here for the lower index peaks, you have only small information depth, and then the information depth increases with a higher order X-ray peaks, and then you have a larger information depth. So we measure this with a wide beam analysis by energy dispersive peaks at the eddy beamline at Bessie in Berlin, and these different energies have different information depth, and therefore the depth distribution can be measured in situ. Something about the experimental details. What do we need? We need a large penetration depth, as large as possible, because we want to see, in the optimal case, through the whole specimen, which means we need a material with a small atomic number to get a low absorption of the X-rays. We need high stresses and large stress fields to be able to image this with our resolution of about 100 microns step by step. Therefore, we need a material with a high yield strength and a high fracture toughness to get large plastic zones and stress fields in front. And we also need a small grain size, because we have to we need more crystals in our spot of the X-rays to not measure in a single crystal case. So here we have our plate, and there we have different textures due to the rolling process. If we look here on this surface, we have large grains. This here 100 microns is the spot size of our XRD. In the ZX direction, we have in this direction small grains, but larger grains in this direction. And if we have a look here on this plane, we have a grain size which seems to be okay. So we can cut our specimen in this and in this direction. And here you see the stress strain curves of our material. It was an aluminum alloy 7075 with yield strength of nearly 500 megapascals and the tensile strength of about 570 megapascals. What we also have seen, if we compare these two specimen orientations, in one case the crack is not growing straight as we want it to have it for a symmetrical stress distribution. Therefore, we selected the ZY direction here. In this case, this is our specimen plan. So these are some experimental details you have to keep in mind. And here, this is our dA over dN diagram. This was from the fatigue testing of a similar specimen, and as I mentioned before, we pre-fatigued our specimen and then we loaded our specimen here at a little bit more than 10 megapascals per meter. And yeah, we also made some calculations. How should it look like? The stresses, sigma xx, sigma yy. This is what you typically see. And we measured only a half field, so only maybe the upper half, and we used then the x-axis as a mirror plane, and therefore our results are symmetrical. This is not what we measured. It's just because of time reasons we were only able to measure the half plane or the half space of the specimen. Yeah, and this is what we expected, and this here is what we got from our measurements. And I think this looks quite comparable if you have a look here on this, especially sigma yy, the stress distribution you typically see if you see these plastic zones and stresses in front of the crack tip. And this is just from one depth, and now we could measure this with the depth resolution. We had here our step sizes, or no, this is the totally measured area. We had in total 450 microns, which is the maximum depth we could reach in our aluminum alloy with the X-rays. We had 90 points per scan, 33 different depths, and one step of loading. So we did, because at the beginning it was a fatigue experiment with overload and something like this, but for this case we just had one. And what you get here is for different information depth, the stresses, and this looks more or less statistical. But if you have a look on the 3D distribution, this looks different. So here again, it's on the surface. Here below the surface, we have an increased area of high stresses, and not really in the middle. This here was the calculation for the middle. This here was the lowest depth we could measure. Then we have again a reduced size of the plastic zone stress distribution in front of our crack. And then we can also make a 3D image of the plastic zone, and this is how the plastic zone looks in 3 dimensions. So the specimen was too thick to be measured completely, but in the middle part where we have the plane strain condition, nothing should change. And what you can see here is the hump I described at the beginning. So we have a reduced plastic zone stress field at the surface, then it increases, and then it decreases to the plane stress condition. This is what we got. It looks more or less symmetrical because we measured this part here, and the rest is all only mirror to get an idea how it looks in 3D. Yeah, and now we think here, this is what I have shown at the beginning, the fracture toughness as function of the thickness of your specimen. This here is well known. Here we have the area where we measure K1C, and then we have the increase of the fracture toughness, and here in this area, region of interest, what happens if you go to very thin specimen. Maybe this can be explained by this behavior of the plastic zone. Yeah, and that's all I want to tell you today about this plastic zone, and to show you if you have your data, even if there was a completely different question at the beginning, maybe sometimes it's worth having a closer look what you can else learn from your data. So I thank you for your attention.
paper is now open for a discussion. Yes, please.
Hi, I'm probably being an idiot, but I thought you could only measure elastic strains with X-ray diffraction. So how do you measure plasticity? Sorry.
Yeah. So what we can measure here is the strain, actually, because we measure it by the strain of the crystal lattice in the XRD. But this is what you get from your different kinds of measurements. You always, sometimes you measure strain, sometimes you measure stress, and then you calculate it at the boundary where you have your yield strength.
Any more questions?
Yeah, maybe if
Yes,
you,
Jacques.
if you go to page on 16, you are comparing the computed and the measured stress profile. So I think the computed one, it looks like a kidney, I would say, and the measured one looks like a butterfly because it goes back like that. Do you have any idea why it's not exactly the same?
No, actually, this we don't know why we have this difference. This is maybe the same as I have shown at the beginning. Here it's also different for the plane strain and the plane stress, and this is what you get also by the C measurements, not only from the X-ray measurements.
Yes. So there is something. Is it possible that with the X-ray measurements, you make some kind of average, whereas in the simulation you just look at the surface, the real surface?
Sure, we will have some average because we have not a steep thickness where we get our information from, because it's due to the absorption, and absorption happens during the X-rays going through the material. So, yeah.
Maybe just a small remark. The middle plane, you're not in plane strain, not in plane strain. You really need a very thick specimen to have plane strain at the center.
Yeah, but
Okay.
but we could not get more information, even if the specimen would be thicker.
Yeah.
The
Because if it's relatively thin, I guess it is in your case, it's not plane strain in the middle.
Yeah, but it's nearly going here.
Yeah, I mean you get this effect.
In a constant. There we are.
Okay, thank you.
Sorry.
Yes.
I want to put about the Miller indices at the beginning. Yeah, like the crystal lattice orientations. You typically people only use 311, but you use all of them every peak.
Yeah.
Could you explain that a bit more? Sorry, I didn't quite get what the profile was on that. Sorry.
Here.
Yeah.
If you have your different peaks, you find them at a different energy. And if you have the peaks 2 to 2, for instance, here at this high energy, then the information depth is higher than for the lower energy because of the absorption of the X-ray. So the X-rays at the higher energy can go deeper inside your specimen.
Okay, so you've basically measured once, but you've got different depths from each peak. Okay. Thank you.
But in this case, sure, you get also for this peak some information collected from the outer areas, because this X-rays are going completely through the specimen, but just to these steps.
Okay, thank you. Any more questions? If not, Mikhail, thank you.